Hello and welcome back to PC Retro Programmer. This video is a continuation of the previous video on CPU registers, and so I recommend watching that first if you haven't seen it already, since it'll make lighter work of today's video. In that video I looked at the lineup of registers on the 8086 and 8088 CPUs, and I talked about the move instructions for moving data between registers and also to and fro between registers and memory. Now, in that video I mentioned that these CPUs don't offer very much in the way of working with two memory locations. Typically you always need to have at least one register or an immediate value or something like that. And in fact all of the instructions on the 8086 and 8088 that take two operands have the restriction that you can't have both operands being memory locations. So that's something to really bear in mind when you're programming these CPUs. Now, I don't mean to imply that there are no ways of working with two memory locations. There are a couple of instructions, a couple of string instructions, which I'll talk about a little bit later, that do actually allow working with two memory locations, but these are very specialized instructions, and they don't actually take the memory locations as operands. They're kind of hardwired in the way that they work, and we'll talk about the details when we get to it. I also don't want you to think that in the history of computing there were absolutely no machines that work with memory instead of registers. If you go far enough back in the history of computing, there wasn't necessarily an advantage to having lots of CPU registers. They could be very expensive to implement, either discretely or in an integrated circuit, and so to keep costs down it was necessary to have a small number of registers. And so, for example, in the PDP-8 they had just one register and a small block of memory called the 0 page, which would contain the other values that you were currently working with. And this was an idea that found a place in the 6502 CPU, an 8-bit CPU that was used in a lot of famous 8-bit machines. And it had a 0 page of 256 bytes. And because this could be addressed much faster than the rest of RAM, that meant that you had an advantage with working with locations in 0 page as operands instead of just general memory locations. So that's one example of where the CPUs would work with memory, preferentially to working with registers because they had so few of them. Now, there are even more extreme examples. If you take the TMS 9900, which was used in the very famous TI 99/4A machine, this was a machine that came out just before the IBM PC. It was a 16-bit machine, and it had a register for an address of a workspace. And this workspace could be moved about in memory just by changing that address. And that workspace contained the values that you were currently working with. So it really preferentially worked with memory instead of registers. This is a bit of an extreme example, and it wasn't necessarily a good design, and certainly by the time IC technology took off, it was definitely not a good design, as the registers were much faster to work with. Anyway, getting back to the topic of today's video, what I want to discuss first is all of the 8086 and 8088 instructions that work with all of the general purpose registers in those CPUs. There's a whole load of these that are all very basic instructions. They run very quickly. And then there are some much more complex instructions that are usually much longer running, and those have very specialized purposes, and I want to talk about those just in generality, and we'll then look at how the different registers then have very specialized purposes with respect to those instructions. Now, the first instruction I want to talk about today is the exchange instruction, and this is fun. It actually has a 4-character mnemonic instead of the typical 3, so it's XCHG. And so this instruction allows you to switch the contents of two things. And this is actually saving you a huge amount of time. If you wanted to do that swap by hand using move instructions, you'd need 3 of them, and you'd also need a temporary register as well. So this does it all just in a single instruction, and it's really fast. Register to register swaps have an execution time of 4 cycles. Now, you have to be a little bit careful about execution times, obviously. In my video on instruction timings, I mentioned that on the 8088 CPU, it can actually take longer to load instructions into the CPU than it takes to execute them. And so we often find ourselves taking the load time rather than the execution time as the cost. And that's certainly the case for fast instructions like this. So in this case, we have 2 bytes of machine code, as you can see. The address goes from 0 to 2 when I assemble this. And 2 bytes is going to take 8 cycles to load in on the 8088. So that is actually the cost. On the 8086, 2 bytes can be loaded in 4 cycles, so there's no problem with the load time there. The total cost is just the execution time of 4 cycles. Now, the other version of this instruction is to switch a register with a memory location. And here we'd be switching the contents of the BX register with the memory location whose address is in SI. And so, as you can see, this is also a 2-byte machine code instruction. There are actually addressing modes that I haven't talked about yet, which would take more bytes of machine code than this, but I'm not going to discuss those today. All these simple addresses, you'll end up with 2 bytes here. But the execution time here is really high because we're dealing with memory. So it's actually 17 cycles plus the cost of the address computation. So whenever you deal with a memory location on the 8086 and 8088, there's a little computation that occurs internally called the effective address computation. And the cost of this actually gets added onto the time. So it's 17 cycles plus effective address computation. So really high. Of course, it's doing a read and a write to memory. That's why it's so slow. Now, it turns out there's a third version of this instruction, which is a really highly optimized version that Intel added. It only works for register swaps, and it only works in the case of a 16-bit swap where one of the registers is the 16-bit accumulator, AX. So there's no 8-bit equivalent of this. And the way it works is that you just supply one operand, which has to be a register. For example, I could do exchange BX, and what this will do is exchange the contents of BX with the 16-bit accumulator, AX. So unfortunately, debug doesn't recognize this version, but if it did, this would be just a single byte of machine code. In fact, debug doesn't even recognize that this is the same thing. It actually uses the general 2-byte version for this as well. To get the 1-byte version in debug, you actually have to put the operands in this order with the AX second, and then it will recognize that this is the special optimized version. A good assembler that's trying to save as much time as possible would certainly use the efficient version here. So you can see the address only went from 6 to 7 here, so it's just 1 byte of machine code. And that's going to be a huge saving on the 8088 because 1 byte's only going to take 4 cycles to load in instead of 8, so it'll halve the time. And even on the 8086, this is an improvement because the execution time also is optimized. It's only 3 cycles instead of 4. So if you can use this variant, you really should. So if you have lots of 16-bit register swaps and you can make one of your registers the AX register, that's going to save you a huge amount of time with this instruction. Now, the next thing I want to discuss is a big block of instructions that all work exactly the same way, even down to the number of cycles they take to execute and even the number of bytes of machine code that they take up. So these will include all of the basic arithmetic operations and logic operations that take 2 operands. So when I say basic arithmetic operations, I'm excluding multiplication and division here because those are slow and complicated on virtually all CPUs and usually quite specialized in the way that they operate. But it will include things like addition and subtraction, for example. So I don't need to go through all of these instructions individually in great detail because they basically all work the same way. So I'm just going to go through addition, the add instruction, in detail, and then I'll just list all of the other ones. So the first variant is just for adding register to register. You can either use 2 8-bit or 2 16-bit registers. And all of these instructions that I'm going to show you work with all of the general purpose registers, both 8 and 16-bit. So obviously I can add any 8-bit register to any 8-bit register. You can see that these are 2-byte machine code instructions, and the destination is always on the left, so it'll do the addition of the two values and then it'll store the result in the register on the left. So the other thing you can do, of course, is add to a memory location. So if I wanted to do a 16-bit addition from the BX register into a 16-bit memory location, I could do it like this. Or of course there's also an 8-bit version if I used an 8-bit register like AL. Now I can also go the other way around. I can add from a memory location to a register. For example, 16 bits, I could do something like this. And of course there's an 8-bit version as well, which I won't go into. And the timings of these are really interesting. So the register to register one, that add BX CX, this is an execution time of 3 cycles. Now you really wouldn't achieve that very often. It'd have to run after a very long running instruction where there was plenty of time for the prefetch queue to do its thing and load the instruction from memory. And the reason for this is that loading this instruction, well, it's 2 bytes of machine code, as you can see, and that's going to take 8 cycles to load on an 8088 and 4 cycles to load on an 8086. So you're actually rarely going to achieve that 3-cycle execution time. Now the memory versions are much slower, so it also depends whether you're adding to memory or from memory. When you're adding a register value to memory, you have to first read the value in memory into an internal hidden CPU register, which you don't see, do the operation that you want in the CPU, and then write the result back out to memory again. And so this means that you're doing a read and a write to memory. So that's very expensive. That's 16 cycles plus effective address. Going the other way, from memory to register, is only 9 cycles plus effective address. And of course there you're only reading from memory. You read the value in, do the addition in the CPU, and then write the result into a register in the CPU. So there's no writing back out to memory in that case. That's why it's so much faster. So the next variant of these instructions works with immediate values. So for example, if I wanted to add a 16-bit immediate value, a constant, to the 16-bit register BX, it would look like this. It takes 4 bytes of machine code, but bear in mind that 2 of those bytes are just the 2-byte constant. Now, of course, I can also do an 8-bit addition to an 8-bit register, but Intel have a trick here, and it's one that a lot of people don't seem to know about. Even when I'm adding to a 16-bit register, if I use an 8-bit immediate value, for example 1, 2 in hexadecimal, then instead of being 4 bytes of machine code, it's only 3. And the reason is that there's an extra bit in the opcode for this instruction that it sets to tell the CPU that the immediate value is only 1 byte instead of 2. And it gets better than that. Take a look at this example, FFFC. So you think, well, that's a 16-bit value, right? But it actually does that in 3 bytes of machine code as well. And the reason is, it's actually a small negative value in 2's complement. It's -4 that you're adding there. And that can actually be stored in an 8-bit signed value. And so what it does is it sign extends that 8-bit value back out to a 16-bit value when the instructions run, and then does the addition. So this saves the extra byte of machine code here as well, so also only 3 bytes instead of 4. Now of course we can also add to a memory location, so let's try this first of all and see what the assembler does. And of course it complains because I didn't tell it whether I was adding to the word at that memory location or the byte at that memory location, and it can't tell from the actual value. So here I actually have to tell it whether I mean a word or a byte. So if I do word PTR, now it will know that I'm doing an addition of a word to a word in memory. But I can also add a byte to 8-word location in memory. So let's see what happens here. And notice it's back down to 3 bytes of machine code again. So it uses exactly the same trick with memory locations and immediate values as it did with registers and immediate values. So that's really cool. That optimization works here as well. And of course I can also add to a byte memory location. Let's use DI this time instead. And for example, if I add the byte 12 to the byte addressed by DI, that will work obviously in 3 bytes of machine code as well. So the cost of these is pretty straightforward. It's 17 cycles plus effective address for the memory versions with immediate values. If you write an immediate value into a register, it's 4 cycles execution time. So those are the main variants, and all of the instructions I'll show you will have all of these variants, but there's actually some additional ones as well. And these are special optimized versions that Intel added for the accumulators. In this case, unlike Exchange, which only worked with the 16-bit accumulator, the trick that we had there, all of these instructions that I'm going to show you will work with both the 8 and 16-bit accumulators. So the instruction in question is the one that adds an immediate value. So if I add a 16-bit value to the 16-bit accumulator, then this is done in 3 bytes of assembly instead of 4. And unfortunately, if you add an 8-bit value to the 16-bit accumulator, it doesn't save anything there. So that same trick that we mentioned earlier doesn't work here. Now the other thing is that you can add an 8-bit value to the 8-bit accumulator, and that'll run in 2 bytes of machine code. So that's again a saving of a byte over the general version. So for all the instructions I'm going to show you, these special optimizations will also exist. They're only there when you're working with the accumulators and with the immediate values. Now I already mentioned there's a whole bunch of instructions that work the same way. They take 2 operands, do some operation on them, and store the result in the destination, which is the one on the left. And the first of these was add, that we already dealt with, and no prizes at all for guessing there's a subtraction called sub. This just subtracts the second operand from the first operand. But what happens if you want to extend an addition or a subtraction beyond the 8-bit values or 16-bit values that you worked with? How would you go about that? Well, let's think about how this works with pen and paper. So imagine you're adding 2 multi-digit numbers together. And so the way it works is you start in the first column and you do an ordinary addition of the digits in that column. And if the result doesn't fit in a single digit, then you put a carry into the next column. So usually denote this by adding a little 1 above the next column. Now, the exact same thing happens when we do arithmetic on a CPU in binary. So, for example, if you were adding 2 very large numbers together, you'd start with the lowermost 16 bits of each of the numbers, and you add those together using an ordinary add instruction. And what it does is it sets the carry flag if the result doesn't fit in the destination. So if you're working with 8-bit values, if it didn't fit in an 8-bit register or an 8-bit memory location, then it would set the carry flag. Similarly for 16-bit addition, if the result doesn't fit in 16 bits, the carry flag gets set. So we need a way of taking this carry into account on the next column. And so this is what the add with carry instruction is for. It will do an addition of its 2 operands just as normal, but if the carry flag is set, then it will add an additional 1. And so that's how addition gets propagated along. And of course it also sets the carry flag if the result doesn't fit in the destination, and so on. So it just propagates along with more and more add with carry instructions. Now subtraction works the same way. If you do an ordinary sub, if the result is negative, then normally what you want to do is do a borrow from the next column. And so this is denoted again by setting the carry flag. So sub sets the carry flag, and you use the sub with borrow instruction to take it into account on the next column. So it does an ordinary subtraction of its operands, and if the carry flag is set, indicating a borrow, it subtracts an additional 1. So then we have 3 logic instructions, AND, OR, and XOR, which work with 2 operands each. And basically these are bitwise operations. So what this means is that it starts off with bit 0 of each of its inputs and does a logic operation on those, and then writes the result into bit 0 of the output. Then it goes on to bit 1 of the inputs and takes those 2 bits and does the logic operation on them and writes the result into bit 1 of the output. And then it goes on to bit 2 of the inputs and so on. So it just moves along bitwise, and so this is called a bitwise operation. Now these instructions are so useful that it really takes an entire video to explain all of the really cool applications of these. So that's going to be a later video, but I just want to give you a head start in explaining what the operations actually are. So logical AND takes 2 bits, and if one bit is set and the other bit is set, hence the name AND, then the output bit will be set. Logical OR looks at the 1 bit, and if that's set or the other bit is set, or both are set, then the output bit is set, hence the name OR. And XOR does a similar thing to OR. It looks at whether the 1 bit is set or the other bit is set, but not both. So it's an exclusive OR. So 1 bit has to be set or the other bit set exclusively, but not together. Then the output bit is set. So that's what the operations actually do, but hang on for a later video where we go through all of the really cool assembly tricks you can do with these instructions. So now one thing I haven't mentioned so far is that many instructions don't modify flags. For example, the move and exchange instructions that we already dealt with don't modify any flags, but all of these operations that I've listed here do modify 6 of the flags called the arithmetic flags. So they are the overflow, sign, zero, auxiliary carry, parity, and carry flags. So they all get modified by all of these. Now I'm not saying they all get modified to meaningful values. For example, the logical operations always set the overflow and carry flags to 0. There's good reasons for doing that, but obviously this is less interesting than what the arithmetic instructions do for these. And similarly, the auxiliary carry usually just gets messed up by the logic instructions. It's not a particularly useful flag anyway, in my opinion, but nevertheless, for logic instructions, not at all useful because the result is pretty much undetermined. Certainly the sign, zero, and parity flags do get set to useful values for the logic instructions, and all 6 of them get set to useful values for the arithmetic operations. So let's go through the flags and explain what they mean. I've already talked about carry in the arithmetic case, and I've said it goes to 0 for the logic case. So let's move on to the overflow flag, which is the next most logical one to cover. It's actually pretty similar to the carry flag, but for signed values. Now, the CPU doesn't know or care whether you're thinking about the values as having a sign or not. But if the values did have a sign, the overflow flag would basically be the equivalent of what the carry flag does, but for signed values. Now, the actual technical description of what it does is a little bit complex and not particularly useful, to be honest. Basically, it XORs any carriers into and out of the highest bit in the operation. So that's the technical description, but you really don't need this because basically the flags are used with the conditional jump instructions, which all have really clear English names, like jump if greater than or equal to, so JGE, or JLE for jump if less than or equal to, or so on. And so you don't really need to know exactly how these flag bits are set in all cases if you're just going to use them with the conditional jump instructions. Now, the next most logical flags to cover are the sign and zero flags. So these are useful in both the logic and arithmetic cases, and they get set if the result is either negative, in which case the sign flag will be set, or 0, in which case the 0 flag will be set. So from this you can tell whether the result of any computation was negative, 0, positive, less than or equal to 0, or greater than or equal to 0, just by looking at these two bits. So really useful flags. And so then there's two additional flags, the auxiliary carry and parity, which are far less useful in my opinion. And these are kind of hangovers from the 8-bit era. In fact, they only really consider the lower 8 bits of a computation. And the parity flag basically counts up the number of ones in the binary representation of the result. And if it's an even number of ones, this is called even parity, the parity flag gets set. So yeah, I'm not exactly sure where you'd use that. Then there's the auxiliary carry, maybe slightly more useful. So basically a byte is thought of notionally as being divided up into two nibbles, the low 4 bits and the high 4 bits. And if there's a carry out of the low nibble into the high nibble, then the auxiliary carry flag gets set. So I guess if you're really working with 4-bit values, this could be useful, but it has limited usefulness, I have to say. I've never personally used it for anything. But anyway, that is what the flags do, and as I said, there are instructions that are flag safe, that don't modify any flags, and other operations that do modify flags. Now, to finish out this video, what I want to do is discuss a handful of instructions which are in some way related to the ones that we just saw. And the first of these are the increment and decrement instructions. So what these do is that they add 1 or subtract 1 from a location. So it's just as if you were doing an addition with an immediate value of 1 or a subtraction with an immediate value of 1. So let's see an example. So for a register example, I could take, say, inc ch, and this would just add 1 to the ch register. Or I could do a decrement, and let's say I wanted to decrement a byte location in memory. Let's take bx to be a little bit different, and there that would decrease the memory location that is addressed by bx. Now these two instructions work the same way as an addition or subtraction with an immediate value of 1, but as you can see, there are only 2 bytes of machine code each, and so this means you have a saving of 1 byte of machine code in each case, which is really quite a substantial saving. Now I say they work the same as addition and subtraction. They do, with one exception, and that is that they don't touch the carry flag. And this is really critical in loop iterations. So if you had a loop counter that you were keeping up to date every iteration using an increment or decrement, then that loop counting wouldn't affect the carry flag. And this is really important for something called carry propagation. So supposing I'm trying to add a small constant value to a very large value, a value that has many bytes. And so I add the small value and there's a carry, and I want to propagate that carry all the way along the entire large value. And so the way I'd normally do that is just to use a whole bunch of add with carry instructions in a loop. But the problem with that is if the carry flag were messed up by the loop counting, I wouldn't keep the carry between iterations for the add with carry instruction. So that's why increment and decrement don't touch the carry. It's so that you can do arithmetic, in particular addition and subtraction, without messing up the carry every iteration of a loop. Now these two versions here are just the standard versions of inc and dec, but there's actually a highly optimized version which works with 16-bit registers. So let's take a look at that. For example, I could increment the AX register, that's 16 bits, so there's only 1 byte of machine code in this case. So these really save a huge amount. Not only that, but the actual execution time of these is just 2 cycles. So these are, I think, the most efficient instructions in the entire instruction set. But as I say, they only work with 16-bit registers. Now the next two instructions that I want to look at are the compare and test instructions, and these are for checking a condition. So in the case of the compare instruction, you're checking an arithmetic condition. You're usually comparing two signed values or two unsigned values, and this is doing an arithmetic comparison of the two. In the case of the test function, it's for checking a logical condition. So typically what you're doing is testing whether certain bits of a value are set or not. And so these are usually used along with a conditional jump instruction, and based on whatever condition you're checking, it will do a jump then to some particular portion of your code. So I'll come back to these when we discuss the conditional jump instructions and control flow, but I just wanted to give you the heads up that the way that the compare instruction works is it basically does a subtraction. In fact, compare is identical to the subtraction instruction, except that it doesn't write the result out. So it still modifies all the flags as though you'd done sub AX BX, for example, but it doesn't actually write the result out to AX, so it doesn't modify any registers or memory locations. Now, the interesting thing about compare is its cycle counts, its execution times. It still has the three versions of the instruction exactly the same as the subtraction instruction, including the highly optimized version that works with the accumulators and immediate values. But in the case where you're comparing a memory or register with an immediate value, for example, if I did compare word PTR with an immediate value, let's say 1, 2, 3, 4, this only takes 10 cycles plus effective address, which is a big saving over using an actual subtraction instruction. And the reason is that it doesn't have to write the result back out to memory after doing the subtraction. So that's where the saving comes from. But bizarrely, if I do exactly the same thing and do a comparison of a memory location, this is the main version of the function now that compares a memory location with a register. This version takes 16 cycles plus effective address, and this is really weird because it doesn't have to write the result back out to memory after the subtraction, so it really should be faster. But according to the 8086 book by Rector and Alexey, this doesn't have that optimization. So I don't know whether this is because they just ran out of silicon in order to be able to implement this really efficiently. It's just a little bit of a mystery, to be honest. Now the test instruction is even a little bit more bizarre with its timings. So it also has three versions, just like a logical AND instruction, including the highly optimized version for working with an accumulator and an immediate value. But in the case of a version where you're doing a logical AND with an immediate value, for example, I could do test, let's say word PTR BX with, let's say 1, then this actually takes an additional cycle over what the compare instruction takes. No idea why. And similarly, if I do test BX with 1, this takes an additional cycle. So it's 5 cycles for this one instead of 4. So I don't know why it has to take longer to do this. Again, I presume that they just weren't able to optimize this in silicon because they ran out of space or something like that. The other slightly bizarre thing about this is that the main version of this operation, which could normally compare any two registers or any register with a memory location, is slightly crippled, and it seems that it's crippled in order to prevent you from making a mistake. So in particular, the version which would compare a memory location, let's say BX with a register like this, this version doesn't technically exist in machine code. And the reason for that is because presumably they wouldn't be able to optimize this in silicon to save the write out to memory after it's done. For some reason they're just not able to do that optimization, and so this version doesn't exist. In fact, debug accepts it, but what's really happening at the machine code level is it's doing this instead. Now, it doesn't matter which order we have the operands here. It's not like compare, which is doing a subtraction where the order of operands matters. It's just doing a logical and the order doesn't matter. So it really just replaces it with this version where the register comes first. So that's a slight quirk, an interesting quirk with this particular instruction. This version takes 9 cycles plus effective address, which is what you'd hope. It's saving that additional write out to memory, and so that's why it can do it a little bit faster. So that's the test and compare instructions. And the final instructions that I want to look at are the shift and rotate instructions. And there's quite a lot of these, so I'm just going to cover the left shifting and left rotating versions. And basically you can know that there's a right version for each of these. So the shift one is shift left, for example, SHL, and if I did a right shift, it'd just be SHR. So you always just replace L with R if you want to go in the other direction. So what this instruction does is shift a memory location or a register left by 1 bit. And so basically in binary arithmetic, this would have the effect of multiplying the value by 2. And the flags are updated. Basically the overflow and carry flags get updated. So whatever bit gets shifted out at the top when you do a shift left goes into the carry flag, and whatever bit gets shifted out at the bottom will end up in the carry flag when you do a shift right. So there's also another version of these that will take n bits and shift by n bits. So you put the value n in the CL register like this. And so that means you can do a shift of between 0 and 255 bits, though obviously when you do a shift by more than 16 bits, the entire register is just going to be set to 0. So then there are instructions for doing rotations. So a rotation is just like a shift, except that the bit that gets shifted out ends up back in the other end of the register. So in an 8-bit case, it would shift out one end and back in the other, and in the 16-bit case, it'd do a 16-bit shift and take the bit out one end and back in the other. And of course, you can also do n-bit rotations using a value n that you put in CL. Now, these also update the overflow and carry flags, and whatever was the last bit that was shifted out one end and back in the other ends up in the carry flag. And this is really useful because, for example, if I shift right by 1 bit, and that bit that gets shifted out ends up in the carry flag, this tells me whether the value that I shifted was odd or even. So this can be really useful in a whole load of different situations. Now, it turns out that there's another really weird rotation that actually uses the carry flag as well in the rotation. So there's RCL, and what this does is a 17-bit rotation effectively. But this is probably a pretty bizarre thing to want to do. And in fact, this instruction exists for another reason entirely. It's best thought of as a shift, just an ordinary 16-bit shift, where the bit that gets shifted in at the other end comes from the carry flag, and the bit that gets shifted out ends up in the carry flag. So that's the better way of thinking of it. Think of it as a shift where you get to control what gets shifted in and you get to capture what gets shifted out. And the reason this instruction exists is to extend a shift beyond the 8 bits or 16 bits or whatever it is that you're working with. So if I wanted to shift a 32-bit value, I could shift using the ordinary shift left instruction, and whatever gets shifted out would go in the carry flag, and then in the next 16 bits I would use the RCL instruction, and so that would shift in that carry that I shifted out in the previous instruction, and whatever gets shifted out at the other end will go into the carry flag, and so I can just extend a shift as long as far as I want using this instruction. So that is for shifting and rotating. Now there's actually an additional instruction, and that is for arithmetic shifting. Now basically all the instructions that I just talked about are for shifting and rotating unsigned values, but you can actually do a shift of a signed value, and this is done using SAR. So let me say that the shift arithmetic left exists for most assemblers. It actually doesn't for debug for some reason, so it just says that's an error, but for most assemblers SAL will exist, but it does exactly the same thing as SHL. It just shifts a 0 in at the low bit. But SAR preserves the sign after doing the shift. So in other words, if I have a negative value, it'll still shift it right by 1 bit, but it will shift in a 1 if the value was negative, and so that keeps the sign the same. So in other words, you can use SAR to divide a negative value or a signed value by 2. And it will keep the sign the same. So if you started off with -4 and shifted right by 1 bit using SAR, you'd end up with -2. So this is really useful for signed arithmetic. Now the timings for these instructions are kind of interesting, and unfortunately they're not very good. There is no efficient barrel shifter in the 8086 and 8088 CPUs. So although 1-bit shifts are quite efficient, in fact for a register shift or rotate it's just 2 cycles execution time, and for memory it's 15 cycles plus effective address, which is pretty good for a 1-bit shift. The n-bit shifts are unfortunately not efficient at all, and basically for a register shift or rotation it's 8 cycles plus 4 times n, where n is the number of bits that you're shifting by, the value that you put in the CL register. So 8 plus 4 times n, so really slow. And in other words, the instruction takes longer depending on how many bits you're shifting or rotating by. And the same for memory, it's 20 cycles plus effective address plus 4 times n. Now on later CPUs they actually had a really efficient shifter that would do all of the shifts or rotates in essentially a constant amount of time, but here the instruction time depends entirely on the value in CL. So if CL is 255, a register shift is going to take 8 plus 4 times 255 cycles. Now the only advantage to that is that you can use this for short delays because the timing depends on whatever value is in CL. So otherwise it's unfortunate. It means that n-bit shifts are really inefficient on these CPUs. On the other hand, the alternative often is just doing multiplication. So if I wanted to multiply by 16, that's going to take at least 71 cycles. But multiplying by 16 is the same as doing a shift left by 4 bits, and so that's only going to take 8 plus 4 times 4, which is 24 cycles. So it's much more efficient to do an n-bit shift than it is to do multiplication by a power of 2, and same for division by a power of 2. So that's really what these instructions are useful for on the 8086 and 8088. Now, as I said earlier, all of the instructions that I've shown you today work for all of the general purpose registers. But in the next video, I'm going to show you a bunch of instructions that really only work for certain registers, and so they give those registers very specialized purposes. And we've already seen the first example of that here. The shift and rotate instructions, when you're doing an n-bit shift or rotate, you have to put the value n in the CL register. You can't use any other register for the value n. And so that is the first case where we've given a register a specialized purpose. The CL register is used for containing the n of an n-bit shift or rotate.